Evie and Teresa are at a playground. Evie is sitting on an initially stationary merry-go-round. The merry-go-round has a radius of 2.5 meters, and Evie is sitting 1.5 meters from the center. Teresa, who is not on the merry-go-round, grabs the bars at the edge and runs in order to give it some angular acceleration. Evie reaches an angular speed of 14 radians per second after 21 seconds. What is the average angular acceleration applied by Teresa? Suppose the merry-go-round can be modeled as approximately a solid disk of mass 130 kilograms, and Evie can be treated as a point, since she's tucked up small compared to the size of the merry-go-round, of mass 44 kilograms. Also assume any other forces besides Teresa's pull are comparatively small enough to be ignored. What is the average torque applied by Teresa, and what is the average force applied by Teresa? This problem will focus on using angular kinematic equations, the concept of moment of inertia, and torque. Now let's look at a sketch of the situation. Always good to start with a picture. We have a bird's eye view here of our merry-go-round disk, and we've drawn just a dot here to represent Evie, and here we see Teresa on the outside applying a force running, which creates this rotation, this angular acceleration of our disk. We'll also then fill in what we know for our variables and what we're looking for. We're told that the merry-go-round is initially stationary, which means it's not rotating. This here is the Greek letter omega, which means angular speed or angular velocity, and its units are radians per second. So since it's initially stationary, our initial angular speed is 0. It's not rotating. And then our final angular speed is 14 radians per second that we're told here. It takes 21 seconds to reach that speed. And what we're looking for, that average angular acceleration, that's the Greek letter alpha that represents angular acceleration. This is one of our angular kinematic equations, and it shows the relationship between angular velocities and angular acceleration in time. In other words, it tells us if we have an object or a system that is initially rotating with a particular angular speed, omega naught, and then there's some acceleration, angular acceleration applied for a given number of seconds, this is the final angular speed that will be reached after that number of seconds. And this gives us a relationship between the three things that we know and the one thing that we're looking for. So if we plug everything in, we get that the merry-go-round's angular acceleration is 0.67 radians per second squared. Remember, with these units of radians per second squared, we can think of this as radians per second, because that's what this is telling us. It's telling us how much angular speed is gained each second. So our speed is increasing 0.67 radians per second each second. Now let's consider the next question about torque. There are two different equations that we can consider for torque. We have the torque due to one particular force, where we look at the force itself crossed with the distance of the force from the axis of rotation and the angle between them. This is a cross product, meaning that this is going to be biggest when that force is perpendicular to that distance from the axis of rotation. And this will give us the torque provided by an individual force. We don't have enough information to use this formula to determine the torque that Teresa applies because we don't know the force that Teresa is applying. The other way that we can conceive of torque is in that the net torque on a system is equal to that system's moment of inertia times its angular acceleration. In our case, the only force providing torque is Teresa's pull. We're told this explicitly. So this is a much better choice to use to solve for torque because we know the angular acceleration and we know something about the moment of inertia. Moment of inertia, it acts analogous to mass in a linear situation. Moment of inertia, the larger it is, the tougher it is to give something angular acceleration, the more torque it takes to provide angular acceleration. Moment of inertia depends on not just an object's mass, but also its radius, its distance from the axis of rotation, and how that mass is distributed along that radius. So we have different moments of inertia for different shaped objects. The more mass is distributed further from that axis of rotation, the larger the moment of inertia. So compare a solid disk to a hollow cylinder. A solid disk is going to be easier to rotate about its center because it has its mass distributed uniformly everywhere from r equals 0 out until r equals the largest possible radius. Whereas a hollow cylinder will have all its mass located out at the edges and is more difficult to get turning, more difficult to give angular acceleration. So even if two objects have the same mass and the same radius, if one of them has their mass distributed closer to that axis of rotation than the other, it's going to have a smaller moment of inertia and it will take less torque to get it to accelerate. Now let's take a look specifically at the two objects that are rotating in this situation that have a moment of inertia that we need to consider. The two that are relevant in this problem are the moment of inertia for a point mass, which we're told we can treat Evie as, and she's tucked up small and is small relative to the size of the merry-go-round, and the moment of inertia of a disk, which we say we can model the merry-go-round as, one solid disk where the mass is distributed uniformly from the center out to the edge. This will allow us to get the moment of inertia of Evie and the moment of inertia of the disk. What we'll use in the formula is the sum of these two things so that we can determine then the total moment of inertia of the Evie plus merry-go-round system. For Evie's moment of inertia, we plug in Evie's mass and Evie's location from the center, from the axis of rotation. And we get that Evie's moment of inertia is 99 kilogram meters squared. For the disk, the merry-go-round, we plug in the merry-go-round's mass and the merry-go-round's radius, and we get a moment of inertia of 406.25 kilogram meters squared. It should make sense that this is much larger than this one, because the merry-go-round has both a larger mass and a larger radius. This gives us a total moment of inertia of 505.25 kilogram meters squared. We can now use this moment of inertia and our result from the first question about angular acceleration to determine the torque created by Teresa. When we fill in the moment of inertia back into this equation for torque, and then we also multiply by our original answer for the angular acceleration, we get the net torque provided by Teresa, which is 338.51 Newton meters. Now we can take a look at the relationship between torque and force, because the third and final question asks us, what is the force that Teresa puts on the disk, on the merry-go-round? We now know the torque is that 338.51, and we also know the location at which she is applying the torque. But how do we actually determine that force? We need a little bit more information. Let's go back and look at a diagram of the situation. We know that the force that Teresa creates is what gives the merry-go-round the torque. We know this torque, that was the second question, and we also know the location at which Teresa is pulling is out at r equals 2.5 meters. She's grabbing onto the very edge. So if we just know this angle theta, we can determine this force that Teresa applies. What does this angle represent? This angle is between R and F. R, the lever arm, is the distance from the axis of rotation to the location of the force. So in our case, if the force is being applied where it's drawn, this is our R. If we're pulling tangentially, which we're told Teresa grabs the handle and runs with it, that's a tangential pull, that's tangent to that circle, then this is a right angle, which means that our theta is 90 degrees, and our torque simplifies down to just R times F, which means that our force, which we want to solve for, is simply the torque over that radius. We know the force then to be approximately 135 newtons, and we have our answer. So taking a look at our problem overall, we know Teresa's average angular acceleration, which is therefore the angular acceleration of Evie and the merry-go-round, is 0.67 radians per second squared. The average torque applied is 338.51 Newton meters, and the average force applied by Teresa is 135 newtons. That average force of 135 newtons is approximately 30 pounds of force, which is a reasonable amount of force that a person could apply. So this answer passes the test, that it's not setting off any alarm bells that means we may have done our work wrong. Always good to check that as our last step.